Um, Welcome everyone to the seminar. So today it's my pleasure to introduce Manibrata Sen, who's a research fellow at the Max Planck Institute for Chemophysics in Heidelberg. Manibrata originally did his PhD at the Tata Institute before moving to a postdoctoral position in UC Berkeley in this network for neutrinos, nuclear astrophysics, and some other N, NSNQAS, whatever the other N is. And he's before moving to his position now in Heidelberg. So Manibrata has worked on things related to neutrino physics and in particular applications of neutrino physics for supernovae. And today we're going to hear about going beyond galactic supernovae to hunt for neutrino physics. So thank you for waking up and being with us, and I'll leave it in your hands.
Thank you so much. So welcome, and as the title of my talk suggests, I'll be talking about how to go beyond a galactic supernova to hunt for new physics. So, of course, in order to go beyond a galactic supernova, it's important to know the basic mechanisms of a usual supernova, right? So that when we do see them and when we do detect signals from a usual galactic core collapse supernova, we understand what it is and we have a good understanding of the basic working machinery of this thing. Let's first begin with a basic introduction to the machinery of a core collapse supernova. So when we talk of a core collapse supernova, it's basically a type 2 supernova, a very massive star, more than 8 or 10 solar masses, which at the end of hydrostatic burning ends up with an onion-like shell with different elements, starting from the lightest element at the top and then going to heavier elements and eventually ending up in iron. You can't form heavier cores than heavier elements than iron because it's energetically unfeasible to put more energy into it and then produce more heavy elements, simply because iron has a much higher binding energy than all other elements. Now, as the iron core starts growing in more and more in mass, it's up to a certain point. It's of course supported by an electron degeneracy pressure that exists inside. Now, this is a very massive shell, but at some point, this degeneracy pressure is overcome by gravity, and this initiates a collapse. So this leads you to the second phase where the entire material starts imploding inwards, thereby increasing the central density of the core. This goes on for some time until a point reaches when the central density reaches almost nuclear densities, and this leads to resisting of the further infall. Because nuclear densities are higher, the strong forces start operating, and this resists further infall of material. And eventually what happens is that because of this, a shock wave is launched. And it is believed that it is this shock wave that leads to a successful explosion. However, our experience with simulations have told us that this process, like going from this step to this step, is not very straightforward, because as the shock wave is launched, the shock wave loses out on its energy as it dissociates material outwards and it stalls. And we still don't have a very good understanding of what causes a successful explosion, as in what leads to the shock wave re-energizing and then causing a successful explosion. We believe that one of the major reasons can be neutrinos, because in this entire process, a lot of neutrinos are emitted. A lot of MeV scale energy neutrinos are emitted, and almost the entire binding energy of the star is given away through neutrinos. And it is our understanding that these neutrinos are mostly responsible for re-energizing the shock wave and causing a successful explosion. That is precisely why we are quite interested in studying neutrinos from a core collapse supernova, because our understanding of these neutrinos would directly give us a picture of what happens inside the core collapse supernova. But what we do know for a fact is that a huge amount of neutrinos are emitted. If you look at the timestamp of the neutrinos, they go on for almost a period of 10 seconds and can even go on longer for hundreds of seconds. And broadly, there are three phases that you can categorize it into. There is a neutronization burst phase, which is mostly characterized by electron neutrinos, and which goes on for around 30 milliseconds or so. This is this peak phase. And this is followed by an accretion phase, which is when the shock wave stalls. And this leads to more or less similar types of emission for all flavors of neutrinos. And then you have a surface emission of cooling, which goes on for 10 seconds and so, and that can go on for even longer. And this eventually leads to cooling of the star. Now, for this talk, for the diffuse supernova neutrino background, we would be mostly focusing on this part, which is the cooling phase, which basically is characterized by neutrinos emitted over a period of 10 seconds or even longer. And this is mostly characterized by a thermal spectra of neutrinos. So you can treat the neutrinos as thermal fermions which are being emitted. And this is what we will consider for most of our studies. Now, of course, all this is something that we understand from simulations, but we also happen to be lucky enough that we have data around 1987. We did receive we did detect around 30 neutrinos from supernova 1987A, which was not really galactic, but close to our galaxy in the Large Magellanic Cloud. And although there were only 30 events that were detected, even till that, we use those 30 events to put some of the strongest bounds on neutrino properties. In fact, the strongest bounds on almost all the properties of neutrinos that we get come from these 30 events, simply because these neutrinos have come from a very, very long distance. And detecting these neutrinos allow us to access a baseline that we cannot access otherwise in our Earth or in any of our terrestrial labs. That is precisely why it makes all the more sense to study these neutrinos, because once we detect them from a future galactic core collapse supernova, this is going to give us the best bounds on almost all properties of neutrinos, that as well as on other fundamental particle physics properties that one can think of. And that would be one of the major motivations for studying neutrinos from a core collapse supernova. But then there is a catch. A galactic core collapse supernova is extremely rare. In fact, on an average, the number varies from like 1 to 3 per century, and this also has a large error bar. So it might happen that there would not be another supernova in the next 50 years or so. So what do we do? Of course, one option is we wait for a lifetime and something happens and then we are happy. Or we can be more inclusive and we can go beyond our galaxy, because once you start going beyond our galaxy to further and further distances, the number actually increases, as you can see in this very nice cartoon. If you go to distances of the order of megaparsec, the number can actually, the rate can actually be almost as big as 1 per year. Of course, you end up getting lesser and lesser events because the flux goes down. But if you're adventurous enough to go even further beyond, to all the way up to the point of star formation, let's say gigaparsec distances, then the number of supernovae is drastically large, to the order of almost 1 to 10 per second. And this is a very, very big number. Of course, the number of neutrinos go down drastically. From one supernova, you would receive almost a number of neutrinos would be even much less than 1, simply because the distance is huge. But then if you integrate over time and you take into account all the supernova that have happened from the time of star formation, then the cumulative neutrino flux is not negligible. And that is something that can be detected. And this is exactly what is known as the diffuse supernova neutrino background. And also sometimes in the literature, it's known as the relic supernova neutrino background. This is in contrast to the cosmological neutrino background, the cosmic neutrino background that we know. This is also an ever-permeating flux of neutrinos that is there. It comes from all over. It's an isotropic flux of neutrinos, and it's there. It's a series of MeV scale neutrinos that is coming from all possible supernova that have happened in our galaxy. And there is a big quest in trying to detect these neutrinos. Once these neutrinos can be detected, as I will discuss in this talk, this will open up a new frontier in neutrino astronomy. So how do you theoretically estimate the DSNB? So one simple way of doing it is by trying to understand that the neutrinos are coming from a very, very long distance. They're coming from cosmological distances. So it's not just straightforward to take the neutrino spectra and calculate the number of events. One needs to take into account the fact that there is a certain rate of core collapse supernova happening in the universe. And also the neutrinos are traveling over cosmological distances. So the underlying cosmology also starts playing an important role. So in order to estimate the spectra of supernova neutrinos, there are 3 ingredients that come into play. Of course, the first thing that you need to know is the neutrino spectra from a core collapse supernova. This is typically something that is given from simulations. And as I told you, simulations roughly agree with the 30 events that we saw from supernova 1987A. So we can trust the spectra that comes out from simulations. And roughly one can characterize the spectra in general by a quasi-thermal distribution that looks like this. This is more like a pinched Fermi-Dirac distribution. And if you set alpha to a value like 2.3 or some alpha to a value like 2.3 or something, you roughly reproduce a thermal spectrum. So this is the neutrino spectra from a core collapse supernova that you would get. You would also need to understand the rate of supernova that happens in the universe. And this rate of core collapse supernova, as I would discuss later, depends on 2 factors. It depends on the rate at which stars are formed in our universe, and also the distribution of massive stars in our galaxy. And of course, you need to know the underlying cosmology, because that gives the redshift factor and how neutrinos are redshifted as they travel over energy. Once you get this, you integrate this over all possible redshifts up to the point of the redshift of star formation. And this gives you the spectra of neutrinos of a given flavor that you would get from this DSNB. Now, so far, so good. The question is, how well do we understand all these three ingredients that go into it? So let's first go into the first ingredient, the underlying cosmology. Now, underlying cosmology it's safe to say that it's pretty well understood. We have a very good measurement of the Hubble parameter, the Hubble function, which basically depends on all these parameters. And this is a snapshot of the data from the 2018 Planck data release. And as you can see, these parameters are more or less well measured. Of course, we know there is some uncertainty in the Hubble parameter itself, but that really doesn't play a big role in this estimation. Moreover, this parameter, as you can see, it essentially provides a normalization to your spectra. So it's important to keep this in mind. The second ingredient is the star formation rate. Now, the star formation rate is a very interesting measurement because there are basically two ways to make the star formation rate, and this is eventually what goes into the rate of core collapse supernova. So what people have done for the past 40, 50 years or so, they have made optical measurements in different wavelengths, in the UV, in the infrared, and so on. And they have tried to get a data set for the star formation rate as a function of redshift. And this is basically the data set that you have. And once you have this data set, and these are from different sorts of measurements that you can see out here, one can do a parametric fit to this data. And this parametric fit is popularly given as a function like this. It essentially depends on some normalization. And then there are spectral breaks, which are characterized by these redshifts, Z1 and Z2, which are basically these points where the spectra breaks. And there are also slopes of the spectra, which are basically given by these parameters alpha, beta, and gamma. So this is purely a theoretical fit, which is just given to fit this data function. And there are, of course, error bars on this. So these error bars are almost up to a factor of 40% or so. And as you can see, you can take some fiducial value, and there are some error bars that are available. And this, once you take this into account, you can basically calculate the rate of core collapse supernova, which is essentially a product of this star formation rate, and also a function that essentially gives you the distribution of massive stars in the galaxy. So this is basically given by this initial mass distribution function. This is essentially some inverse function of the mass of the star. There is some parameter, but this parameter also varies over some range. But the important thing to note is that it's an inverse function. So the more massive stars contribute less, which is why in this integral, the upper limit doesn't really matter much. The lower limit roughly starts from the mass at which you expect core collapse supernova to go off. So this is around 8 solar masses. The upper limit is roughly truncated at the point where you do not want to include neutrinos from failed supernovae, or supernovae which go into a black hole. But if you want to include this, you can go all the way up. And this is essentially normalized up to all the way up to 100 solar mass stars. One can go even larger, but as I said, this upper limit does not really matter much. And once these two things are known, they can be combined to give you the rate of core collapse supernovae that takes place in the universe. One can also alternatively do a direct measurement. You look at the sky, you see the rate at which supernovae go off, and then you try to measure the rate. That has also been done. And it so happens that the rate measured from direct measurements and the rate measured from these observations roughly differ by a factor of 2. So this is still an uncertainty that exists in the literature, and people have been trying to figure out why this factor of 2 exists. The third and the most important ingredient for us would be the neutrino spectra, which, as I said, is fairly well known from simulations. One can basically treat it like a quasi-thermal spectra. And if you are mostly interested in this 10 seconds of cooling phase spectra, you might as well treat it as a thermal spectra. This spectra, of course, has to be processed by different kinds of neutrino oscillation effects that take place inside the star. And as you might know, the neutrino oscillations inside a core collapse supernova is an extremely complicated study, because one needs to take into account neutrino self interactions as they travel inside the star, because the neutrino density is extremely large. And as a result, neutrino self interactions end up making this problem a very complicated nonlinear problem. However, if you're interested in the phase where the three different, the nu E, the nu E bar, and all the non-electron flavored neutrinos, which we call nu X, if these three are roughly identical in normalization and in shape, then you would realize that the oscillations would not really make a drastic difference. And this is what is characteristic of this cooling spectra, where the three flavors are roughly, they have the same hierarchies, which is why collective oscillations do not make a big change. They give you roughly like a 10% change in your spectra. So this can be ignored up to first principle calculations. One only needs to take into account the standard matter effect as neutrinos travel through the Earth, which is basically captured by the usual adiabatic MSW transition. And what one needs to know is that under this framework of neutrino propagating through a matter, the heaviest neutrino eigenstate, which in the normal hierarchy would be the nu3 and the inverted hierarchy would be the nu2, they would be emitted mostly as the electron flavored neutrino, whereas the lightest neutrinos would be emitted as the non-electron flavored neutrinos. Similarly, for the antineutrinos, the lightest neutrino would be basically emitted as a nu e bar. So this is the only thing that one needs to remember from this matter transition, that the neutrino that is produced as the heaviest state would essentially be emitted as a nu e. Also, the shape of the spectra can be understood by the average energies that go into this. So this E0 is basically the average energy, and that is related to the temperature of the neutrinos. And the temperature basically follows a hierarchy of this form. This is somewhat easy to understand. So the electron neutrinos have the lowest average energy because they end up interacting the most inside the star, because electron neutrinos end up interacting with neutrons, and there are a lot of neutrons inside the star. So the average energy of electron neutrinos is less, followed by the electron antineutrinos, which end up interacting mostly with protons. And then the maximum average energy belongs to the non-electron flavored neutrinos because they free stream the earliest. They interact mostly through neutral current interactions. And this is what basically explains the normalization and the shape of this spectra. So once these three ingredients are well known, you can plug this into your formula. This is a straightforward computation, and you can basically estimate the DSNB spectra that enters into your computation. And this is exactly what you get. So this is an estimation of the DSNB spectra for the nu E, which is given by the orange lines, the nu E bar, which is given by the green dashed lines, and then the nu X, which is this other one. All these things have an envelope, which is basically the uncertainty that comes from your lack of knowledge of the star formation rate. Remember, in the star formation rate estimation, there were these parameters which were unknown up to an uncertainty of 40%. And this uncertainty is what gives you this envelope out here. This is the very nice analytical expression and the spectra for the DSNB. But of course, once you try to detect them, you realize that this parameter space that you're looking at, the energy ranges that you're looking at, is not really very clean, because in these energy ranges, there are a number of other backgrounds that one need to keep into mind. And these backgrounds might as well be much, much larger than this spectra that you're seeing, and they can overcome this signal completely. So what are the main backgrounds that one needs to keep into mind in order to detect the spectra? Of course, one needs the first background that is relevant for us is the solar neutrinos. It's basically the flux of nuis that come from the sun. And this can extend all the way up to 20 MeV. Now, this is essentially a reducible background because in principle, there are two reasons. One, we know that it's mostly nuis, so the other flavors are not really hidden in this background. And secondly, there are ways of detecting, there are directional information that one can use. One can, in principle, to a very good approximation, know from which direction these nuis are coming from the direction of the sun, and then basically reduce this background. On the other hand, the DSNB is an isotropic background. So this can allow you to reduce this background. There are also geothermal neutrinos, which are essentially antineutrinos that come from different elements inside the Earth, like uranium, thorium, and so on. And these are low energy backgrounds. They exist around up to 4 MeV or so. And these are like small backgrounds, and they also can, in principle, be removed. Then there are irreducible backgrounds, which are more difficult to remove, simply because they also look a lot like the DSNB in the energy ranges that they are relevant. So for example, reactor antineutrino. So in all these experiments that we use to detect these DSNB, they are usually very close to a reactor site, a nuclear reactor site, which produces also an isotropic large flux of nu bars. And then these nu bars can extend all the way up to 10 MeV. And up to 10 MeV, these nu bars, they not only overcome the DSNB, but they also look very much like the DSNB. So it's very difficult to remove this nu bar spectrum. Similarly, there is also, we know there are atmospheric neutrinos, which is again very similar and very difficult to remove. But the advantage with atmospheric neutrinos is that they have a very small contribution in the energy ranges that we are interested in. So they basically form like a low energy tail in this region, and they only start growing above 50 MeV or so. But still in this higher energy tail of the DSNB, you can have a large contamination from atmospheric neutrinos. So roughly these would be the 4 major backgrounds that one needs to contest again. And if you can overcome them, then in principle, you can detect this. Also, if you superimpose all these backgrounds, you would find that there is a certain energy range, which roughly lies between the 10 to 26 MeV region, where the DSNB signal can be somewhat clean because none of these backgrounds actually overlap in this region. And this is the region that we would be interested in. So there are a number of experiments which have been planned or which are running, which have the detection of the DSNB as one of their main goals. So for example, Super-Kamiokande is the forerunner in this business, as I will talk about soon. And then there are experiments like Juno, Dune, Hyper-K, which are supposed to play a major role in detecting the DSNB. In this talk, I would be mostly focusing on Super-Kamiokande and then the first 3 experiments. But I will also mention a bit about Resnova and others as well. So how does Super-Kamiokande detect this, plan to detect this DSNB? What is the basic detection mechanism? So the main channel of Super-Kamiokande to detect the DSNB is essentially inverse beta decay. So they look at antineutrinos coming from the DSNB. They interact with, so Super-Kamiokande is a huge tank of water, and they interact with the protons in the water, giving rise to a positron and a neutron. And what happens in the process is the positron gives rise to Cherenkov radiation, which can be detected. And then the neutron eventually can be captured by a proton, which in turn can go for which can get excited and then release like a 2.2 MeV gamma ray. And you can detect these two signals in coincidences. Once you can detect these two signals in coincidences, you can basically say that this is an event that is caused by a Newey bar. Of course, this is easier said than done. And there are again a number of backgrounds that Super-Kamiokande has to cope with. So the major backgrounds being spallation. So for example, you can have cosmic ray muons that come and atmospheric neutrinos that come and produce these muons, which essentially can hit the oxygen nucleus in the water and basically create another muon. And this essentially mimics the signal of a DSNB, because this gives you the same signatures as you would see out here. And you can also have invisible muons coming from atmospheric neutrinos, where essentially you end up producing muons which do not have enough energy to cause a Cherenkov radiation. And then once that decays, that again produces a signal that is very similar to this. And this sort of and of course you would have atmospheric neutrinos. And these 3 backgrounds essentially kill all the signals that you can get. So Super-Kamiokande currently has been trying to detect this. And very recently, 1 year or so ago, they released their latest data, where essentially, as you can see in this, the red line is basically their latest data, and they are trying to probe the parameter space in the energy and the flux. So they have already ruled out some of these models. So the gray lines are essentially different models of the DSNB depending on what average energy and what alpha parameter you use. And Super-Kamiokande already has probed some regions of this parameter space. Of course, they have not detected anything as of now. But then what they have been trying to do more recently is to reduce these 2 backgrounds, because the spallation and the invisible muon backgrounds are the key players in this. And if you can somehow get rid of this background, then in principle, you can actually go much below and basically reach this entire parameter space. And this is where gadolinium doping plays an important role. This was an idea that was suggested as early as the 2000s by Beacom and Wagons. And the idea is very simple, that in this process where you have a neutron that is produced and a positron, tagging the neutron that is produced is very important. So once you can tag the neutron, then you basically know that this is an event that comes from a Newey bar. And while the proton can capture a neutron, if you add gadolinium to water, then the neutron capture cross-section increases drastically. And this is the basic idea behind it. So if you put gadolinium into your solution, then gadolinium essentially can capture this neutron much more. And then the gamma ray that is also released is a higher energy gamma ray. And you also have a certain coincidence time that can be measured. And this in principle can allow you to tag the neutron and basically very easily identify the inverse beta decay event that you're getting. And this can allow you to reduce these 2 backgrounds drastically. So for example, the spallation background can be subtracted almost completely. And the invisible muon background also goes down almost by a factor of 5. And this leads to basically some region where the signal is quite clean and one can in principle detect this. So this idea is almost ready. So Super-Kamiokande basically has been doping gadolinium into their system, and they have been doing it consistently. And I think they have already started taking data, and they would probably report something soon. But the claim is that if this thing goes on smoothly, then probably they would have a positive detection by the end of the decade, or at least by the middle of next decade, which is already very exciting, because then what we're saying is within the next 10 or 15 years, we would probably have detected the diffuse supernova neutrino background. Remember, this is, in my opinion, this is equivalent to the cosmic microwave background, but for the neutrinos, because this is an ever-present neutrino background, just like the cosmic neutrino background. But whereas the cosmic neutrino background is very, very difficult to detect, this is something that is in principle in the right ballpark value for energies that one can detect it. It's only a game of reducing the background. So once the background can be reduced, in principle, this is a neutrino background that is coming from the early universe, reasonably early. I won't say like the early universe as the CMB or the CNUB, but early universe. This goes up to redshifts of 6 or 7. And in principle, this can be detected. So because of this, there are also a lot of experiments that are underway that in principle is very much interested in this. So I will be talking about two major experiments. One is essentially the Hyper-Kamiokande, which is the bigger version of Super-Kamiokande. And we will assume that Hyper-Kamiokande has agreed to go ahead by doping it with gadolinium. So Hyper-Kamiokande, simply because it's 10 times larger than Super-K, can provide excellent detection prospects. So the backgrounds are roughly the same, but of course, the number of events are drastically larger. So for example, Hyper-Kamiokande can in principle see almost 100 events in the region that we are interested in. So there are backgrounds. So for example, this is the Hyper-Kamiokande signal, as you can see in purple, and the backgrounds are given by, there are this invisible muon backgrounds and the atmospheric backgrounds, and you can see there are these regions where the signal dominates over the background quite a lot. And the other experiment, Hyper-Kamiokande, of course, is a water Cherenkov detector. It looks at the Cherenkov radiation that is produced from the positron that's created. The other experiment that's quite interesting, and this is still under consideration, is an experiment called Theia. So Theia is supposed to, it's a small experiment, and there are two variations of it, and it's supposed to be installed in one of the near detectors of Dune. So this is still under consideration. But the advantage of Theia is that Theia is basically a water-based liquid scintillator detector. What this means is that Theia essentially takes the best of both worlds from a water Cherenkov detector and the scintillator detector. So a water Cherenkov detector basically has very good energy reconstruction possibilities, because you can detect the Cherenkov radiation, you can track it back to the initial neutrino, and you can very well reconstruct the energy of the incoming neutrinos. On the other hand, a liquid scintillator, which basically is a scintillating device which creates a scintillation whenever a charged particle is produced, has a very, very low energy resolution. So what Theia does is it takes a liquid, it takes basically water and then dopes it with a liquid scintillator. As a result, you can essentially use both the properties of Cherenkov rings as well as scintillation to reduce backgrounds drastically. So for example, this is the number of events that Theia would see. Of course, because of its size, the event rates is small, but then Theia basically in the energy range of around 20 to 30 MeV can easily get over the backgrounds, whereas the major background being from atmospheric neutral current events. And this in principle can also be reduced. So a combination of these detectors in principle, and these would all be running in the next 10 or 20 years, a combination of these detectors can in principle be very, very useful for a future detection of the DSNB. Of course, there are, as I said, there are other detectors. Dune, for example, is also going to be a major player in detecting new E events, because these are all based on inverse beta decay technology. They only try to detect new E bars. For new E's, you have Dune as the major player. Then you also have a number of coherent scattering experiments, which are also trying to look to if they can separate out the non-electron component for neutrinos and so on. So there are a number of experiments that are trying to play their part in the detection of the DSNB. But let's not go too much into experiments. The idea is, let's say within the next 10 to 15 years, we do end up detecting the DSNB. And the claim is that with that, there are different multidisciplinary aspects of understanding these supernova neutrinos. So there would be a lot of information that one can gain about particle physics in general, like neutrino physics, neutrino propagation in a dense media, and a lot of information about neutrino properties, which would be the subject of this talk, and even cooling mechanism of stars. So this is something that has come up in a number of topics as well, like how do stars cool in general. These neutrinos also can be used to gain a lot of information about astrophysical stuff like star formation rates, including the life and birth of stars and so on, because the rate of core collapse supernova enters directly into this calculation. Also, as I would briefly show you, they can also act as essentially they can act as distance indicators, because the underlying cosmology plays a role in this. So one can use this to make a measurement of the Hubble parameter. In general, measurement of these neutrinos would basically add to our multi-messenger aspect of doing particle physics, right? Because not only are we getting information about some of these quantities from photons and gravity waves, but we are also using neutrinos as a channel of doing astronomy. And these can basically all open up with a future detection of the DSNB. So the talk would be essentially based on these 4 papers that we worked on, and which basically explores all these different aspects. And in this talk, I would be mostly focusing on different kinds of neutrino properties that one can probe. So let's take a look at the first property. It's a very simple property. We're looking at non-standard neutrino decay. So of course, we know within the standard model, neutrino can decay through a radiative process, but that decay is quite long. I mean, the lifetime is longer than the age of the universe. On the other hand, if one can postulate new particles, like some new scalar or something, which is very weakly coupled to the neutrinos, then the neutrino can decay through a 2-body process like this, or even a 3-body process if energetics are feasible. And then this decay lifetime can be shorter than the lifetime of the universe. And a lot of studies have been taken to try to probe this sort of a decay mechanism in different contexts. The advantage that you have is, because this decay is the lifetime of this decay is something that we do not know, we can use different probes to understand this decay. And for neutrinos that are traveling over very, very long distances, for example, these neutrinos, which are coming from gigaparsec distances, you would have access to lifetimes that you would not have anywhere else in the universe. So this is basically the idea that goes behind this. Now, of course, if you postulate a Lagrangian like this, there are 2 possible decay modes that can happen. One can have a helicity conserving decay, where essentially the parent neutrino, which is decaying, and the daughter neutrino, they have the same helicity. Or you can have a helicity flipping decay, where the daughter neutrino has the opposite helicity of the parent. And in principle, they have different energy distributions. And this can be understood from momentum arguments, that basically the daughter neutrino that is essentially has the same helicity as the parent, they would be emitted preferentially in the direction of the parent spin. So they would have a distribution that goes like 1 minus of cosine theta, so 1 plus of cosine theta. So they would be preferentially emitted in the direction of the spin, whereas the one that goes in the opposite direction would be less preferentially emitted. And this can be translated into an argument about how the energy distribution looks like. Now, the question is, if this sort of a decay takes place, how does this affect or change the DSNB spectra? And the idea, I'm going to illustrate the idea for a very, very simple decay of a 2-body decay of this form, but one can generalize this to more complicated decays. So let's consider the normal mass ordering, where the nu3 is the heaviest state. The nu3, of course, has the least content of electron neutrinos, and the lightest state is the nu1. And let's consider a decay where the heaviest state nu3 decays to the lightest state. Now, we take a hypothetical setup. You have a core collapse supernova happening somewhere. You have a neutrino that is produced. Remember, the heaviest neutrino, and in the MSW scenario, the heaviest neutrino, which is nu3, is produced as a nu3. The nu-E is essentially can be related to the heaviest neutrino, nu3. So nu-E is produced. It eventually emits as a nu3 because there is a separation of mass and flavor eigenstates. Everything decoheres, and the nu3 travels towards the Earth. In the absence of decay, what arrives at the Earth is a nu3, and then the nu-E component is basically just the PMNS matrix element square, which is UE3 square, which in this case is just like 2% of the original flux. So in the normal ordering scenario, in absence of decay, whatever nu-E is produced, what arrives at the Earth is only 2% of that nu-E roughly. Of course, there are contributions from non-electron flavors, but we are not considering it right now. Now, what happens if the neutrino decays, for example, to a nu1? Then en route, the nu3 can decay to a nu1. And then let's say the decay is complete, all the nu3s convert to a nu1. And then what arrives at the Earth is a nu1. And then if you look at the PMNS square, then that is 70% of the original flux. So depending on what the decay is, there can be a huge enhancement in spectra in normal mass ordering. Similarly, if you go to inverted mass ordering, there can be a suppression in spectra. And this can basically be used to understand, or rather to probe the neutrino lifetime bounds. You know what the spectra would be, and then if you see an enhanced or a suppressed spectra depending on the mass ordering, and you assume that mass ordering would already be known by that time from experiments like Juno and so on, one can actually use this information to probe lifetimes which would not be probed otherwise. And if you want to increase this impact more, you can basically take a Majorana neutrino, assume that neutrinos are Majorana, in which case essentially the wrong helicity component also acts like an anti-neutrino. And then an experiment like Hyper-Kamiokande would also be able to see these events. So for example, if you look at the events as a function of energy, the blue line tells you what Hyper-Kamiokande expects for the DSNB in the case of no decay. On the other hand, if neutrinos start decaying with a certain lifetime, then in principle, you see these other colored lines. And this is the same for Theia. And as you can see in the normal mass ordering, you start seeing an enhancement in the number of events in certain energy bins. And you can use this to probe neutrino lifetimes. And basically, you can show that an experiment like Hyper-Kamiokande can essentially probe neutrino lifetimes as large as 10 to the 8 or 10 to the 9 seconds per EV with a reasonably large significance. Of course, not as large as any of the other experiments that are undergoing right now, but because of the uncertainty that exists also in your star formation rate. But they can basically probe lifetimes as large as 10 to the 8 or 9 seconds per EV within significance that is larger than 2 sigma. And this, of course, is done with a 40% uncertainty. So if the uncertainty is reduced, this can in fact go up much more. Of course, the significance is low because the flux is low, but the advantage is that the lifetimes you can probe is something that you cannot probe otherwise. This is what I have been claiming. And this is precisely because the baseline that is given to you is gigaparsec, as opposed to thousands of kilometers that are there for long baseline experiments, or for the solar distance, or even for neutrinos that come from ice cube and so on. The lifetimes that you can probe are not even comparable. Cosmology, on the other hand, as has been shown in these papers, can actually probe lifetimes which are similar to these ballpark values. And so, of course, from cosmology, the bounds can be even like they can be measured with a larger significance. But then the point is, these would be the only sources of measuring lifetimes which are as large, and you cannot measure it in any other. There is no other experiment that would allow you to measure lifetimes that would be so large. And this is something that one needs to take into account when studying neutrino decay, for example. The second example that I would talk about is that of pseudo-Dirac neutrinos. And this is essentially related to lepton number violation in the standard model. So let's take a moment and understand what we mean by lepton number violation in the standard model. So imagine we have 3 active neutrinos, and we want to understand neutrino masses in the standard model. So we add 3 more sterile neutrinos to our system, and then one can write down a generic Majorana mass matrix of this form. So you have you have a contribution to the active neutrinos, you have a contribution to the sterile neutrinos. These are essentially Majorana masses, and then you also have Dirac masses, which are these off-diagonal components. The diagonal components are lepton number violating components, because these are the terms that these are the contributions that come from terms which are lepton number violating. Now, we probably all know about the seesaw mechanism, which essentially works in the limit where these diagonal elements are extremely heavy, in which case you basically get decoupled states. You get 3 active light neutrinos and you get maybe 3 heavy neutrinos. However, one can work in the other limit where these numbers are extremely tiny. What this means is you're working in a limit when lepton number violation exists in your standard model, but it's extremely soft. So it's always the Dirac mass that dominates. But then there are tiny violations of lepton number coming from these diagonal masses. In this limit, something opposite to the seesaw mechanism happens. So what happens is, if you diagonalize your Hamiltonian, you end up getting 3 pairs of degenerate states. So the active and the sterile states come very, very close together, and their mass difference is essentially governed by this tiny quantities. So the picture of your 3 neutrinos, so you have 3 active and your 3 sterile neutrinos, and they start coming very close together. And the picture essentially looks like this. So you have an active state, let's say nu3, and very close to it, you also have the right-handed state, which we call the nu3 sterile. And the mass difference between them is a very tiny quantity, which is essentially given by the product of these diagonal elements and this element. So this quantity delta m square, it's much, much tinier than the usual atmospheric mass square difference and the solar mass square differences. Now, in this scenario, something very interesting happens. Because you also have a very, very tiny mass square difference between the active and the sterile state. So for example, this and this, or this and this, you can have oscillations between active and sterile states, which are governed by this very tiny delta m square. And of course, because the mass square differences is much smaller, these oscillations would only be relevant over very, very long baselines. So if you have long baselines, you can have an active neutrino converting into a sterile neutrino with a frequency which is governed by this tiny delta m square. Now, this idea is not new. This idea is quite old, and they have been probed much earlier on. So for example, people realized quite early on that for solar neutrinos, this can be used to probe delta m squares as tiny as 10 to the minus 12 eV square. This also happens to be some of the tiniest values of delta m square that one can probe with solar neutrinos. Simply again, because of the baselines you get from solar neutrinos, you can probe very tiny delta m square. Atmospheric neutrinos can also be used to probe values which are of course larger and not as large as long as solar neutrinos. And one can also use high energy neutrinos to probe values which are in this ballpark value. But one immediately realizes that if you can detect neutrinos from the DSNB, these are some of the oldest neutrinos that we have. They're coming from the epoch of star formation. And then you can of course use this to probe values of delta m square, which might be even smaller. And so what happens? Let's understand this oscillation due to this delta m square for the DSNB, and then let's see how this can be used to probe tiny values of delta m square. Now, of course, as I said, this would lead to oscillations between active and sterile neutrinos, which are only operative at very, very long distances. Now, typically what this does is this modifies your flavor oscillation probability. So if you want to look at the probability of one neutrino flavor going into another neutrino flavor, in absence of these active sterile oscillations, for neutrinos traveling over very, very long distances, they essentially decohere, and the probability is just given as a product of their PMNS mixing matrix squared. This is standard knowledge. But then if you have extra oscillations which are governed by these active sterile oscillations, then one needs to multiply this with this active sterile oscillation probability, because this is happening over very long distances, so this doesn't get averaged out. And this active sterile oscillation probability can be calculated in the standard two neutrino framework. So you assume one active, one sterile, you calculate the probability. And this is very, very similar to the standard two neutrino oscillation probability. So this looks like this. It essentially depends on the distance that the neutrinos travel, which is given by L of Z. And there are two other length scales that are involved. One is the oscillation length scale, and one is the coherence length scale. Now, if you look at this formula and you assume that the coherence length scale is extremely small, so go to the coherence length is extremely large. So go to the limit where this exponential factor can be set to 1. Then basically this boils down to your standard neutrino oscillation formula, because you just get 1 plus cosine, which is sine square of L over L oscillation. So you get back your standard oscillation formula. But because the neutrinos are traveling over very long distances, you get this additional factor of which essentially takes into account the fact that once neutrinos travel over very long distances, there is a certain coherence length up to which coherence is maintained. So if you think in terms of neutrino wave packet picture, neutrino oscillations essentially take place as long as the wave packets associated with different neutrino mass eigenstates overlap. But as they travel with different velocities, simply because they have different masses, after a certain distance, the wave packets stop overlapping. And then there is no more oscillation. Neutrino oscillations average out at that point. And this distance is essentially what we call the coherence length. So this tells you the length up to which neutrino can maintain its coherence. And beyond, for distances greater than L coherence, they just averaging takes place because the wave packets separate. So you can also see it out. If L is larger than L coherence, the oscillation term kills out completely. And then this one can estimate what these length scales are for our choices of parameters. So for an energy of around 10 MeV, which is the standard DSNB energy, and the delta m square, which we are interested in. So let's say for a distance of around a few gigaparsec, the delta m square would be, the oscillation length would be of the order of a few gigaparsec if you choose a delta m square of around 10 to the minus 25 ev square. This is a very, very tiny value. But for this value, the oscillation length is the length that the neutrinos from the DSNB travels. And similarly, one can compute the coherence length. It also depends on the width of the wave packet that you choose. And this can be done from first principle calculations. And a rough, nice ballpark value would be of the order of 10 to the minus 12 meters. And this tells you that for these distances, the coherence length can be much larger. It can be as large as almost 200 gigaparsec. But of course, if you play around with these delta m square and sigma x, this can be smaller. And if you take these things into account, then what you see is the standard flux undergoes oscillations, of course, once you put in this probability into your computation. So the standard model flux, which is just given as this, once you switch on a tiny delta m square, let's say of the order of 10 to the minus 25 ev square, you see these rapid oscillations as is given by blue out here. Once you start increasing these oscillations, delta m square, what happens is your oscillation frequency starts increasing, and as a result the oscillations become, so two effects happen. So once you increase delta m square, the oscillation length decreases, which means the oscillations become more rapid, but also your coherence length also decreases. So your averaging effect also starts happening. So the number of events also start going down. And if you go to values of like 10 to the minus 24 EV square, you see that the number of events have almost gone down by a factor of 2, which basically means that this averaging effect comes out. So if this just becomes a factor of 1, then you just get half nothing, because this guy goes out and you just get half out here. So your number of events go down by a factor of 2. So it's a combination of these two factors that come into play. And this again, we demonstrate out here, but this is something that I already told you, that it essentially depends on two factors: whether you start increasing delta M square, which basically reduces your number of events, but also starts inducing a lot of oscillations, or you can play around by changing sigma x, which does a similar thing. And the idea is, because of these oscillations that would exist, they are not a normalization change, right? They essentially induce shape changes in your spectra. You can use this to probe delta M square as tiny as 10 to the minus 25 EV square or so. And this would in principle be something that can be detectable in experiments. So in this plot, I show you 3 snapshots. It's essentially a sensitivity study in different experiments. So the left plot is for Super-Kamiokande, this is Hyper-Kamiokande, and this is Theia. And you see the sensitivity as a function of delta M square for different values of the sigma parameter. So let's just look at the blue line, which is for a sigma parameter where decoherence is not very important. In this case, you see that Super-Kamiokande already with gadolinium and 10 years of data taking can basically probe values of delta M square like 10 to the minus 25 EV square with a sensitivity which is larger than around 3 sigma or so, like delta chi square more than 10. On the other hand, Hyper-Kamiokande and Theia, because of different reasons, like Hyper-Kamiokande is much larger, Theia is more sensitive, can probe these values with a much larger significance. I mean, the delta chi square value just shoots through the roof. So these experiments, of course, are futuristic. They would come up in the next 20 years or so, would allow you to probe delta M square much smaller than what has been probed in other experiments. This can be clearly understood if you look at the landscape of oscillations out here. So on the y-axis, you have the different energies that different experiments can probe, and the x-axis gives you the different baselines that different experiments can probe. So for example, reactors would probe energies of around a few MeV, and they have baselines of around a few kilometers. On the other hand, accelerators, atmospheres lie somewhere out here. And then these dashed lines are the values of delta M square that these different experiments are sensitive to. So for example, these are all sensitive to delta M square solar and delta M square atmospheric, which all lie out here. On the other hand, solar neutrinos can in principle be sensitive to delta M square of around 10 to the minus 12 EV square. In this landscape, the DSNB basically lies somewhere out here. So we are probing almost the extremist part of the parameter space, which cannot otherwise even be probed. You can use neutrinos from supernova 1987A also, and because they're not coming from such a long distance, they also probe delta M square of around 10 to the minus 19 EV square. But this is swamped by the DSNB, which basically probes this region. And this is one of the tiniest value of delta M square that can be measured by any other experiments so far. So this would be another scenario where the DSNB can be used to probe very extreme properties of neutrinos. And remember, this boils down to probing lepton number violation, because this delta M square is basically proportional to the diagonal elements which were signifying lepton number violation in your theory. And this tells you that this sort of an experiment and measuring the DSNB can allow you to probe how small lepton number violation can be in your standard model. And this can be one way of probing this. The third and final thing is somewhat exotic. And then what I'm going to try to convince you is that although this idea exists, it might be more difficult to do immediately, but there is a possibility of using neutrinos from the DSNB to also probe the origin of neutrino mass, how neutrino masses originated. So what do I mean by this? The basic question that we want to understand is the following: can the neutrino mass be redshift dependent? Now, this is a question that has been existing in the literature for quite some time. And the idea is the following, that all the data that we have so far, they do not tell us that neutrino masses have to be non-zero at the time of, at the epoch of the CMB formation or even later. Because all Planck data, all CMB data and so on, they're perfectly consistent with zero value for the neutrino masses. The bounds are always there are always some upper bounds, and we do not get that this is always greater than zero. So in principle, the neutrino mass, the oldest measurement of non-zero neutrino mass in principle are solar neutrinos. So because that is where we have detected neutrino flavor transitions and so on, and also oscillations. And then we can say that, okay, neutrinos can have a non-zero mass. But you go older, you have no such measurements which can tell you that neutrinos have to be have non-zero masses. So the question is, can the neutrino mass be redshift dependent? And can it be possible that the neutrino masses were zero up to a certain point, and then because of some physics that we stay agnostic of, it can be some phase transition and so on, neutrino masses switch on? So this is an idea that had been explored in these papers. And one thing that they did was they basically took all possible data from cosmology, like CMB, Planck data, polarization and lensing data, and so on, baryon acoustic oscillation data, type 1 supernovae data. And then they essentially broke the neutrino sum over mu. They categorized this as a function of redshift. So they took the sum over mu in different redshifts, and then they tried to put constraints on this quantity from these different data sets. And what they found was, if you go to very low redshifts less than 0.1 or so, this bound becomes loose. So this bound from a value which is less than 0.3 or something, it goes all the way down to 1.46. And they say that this bound in principle it arises due to the degeneracy that exists between some mu and the dark energy value of the dark energy density. However, they can also claim that there are models, which they also discuss in this paper, in which if the neutrino mass is generated at a low enough redshift, then these can allow for the neutrino mass constraints to become loose in the early universe, in the late universe, basically at redshifts which are less than 1. So in principle, the question that we wanted to ask was, let's say this sort of a scenario exists. We do not know whether the physics that goes into this it at all can be realized or not. But let us imagine that this something like this can happen, and if the neutrino mass can actually be a function of redshift and it's different from what we observe now, are there other ways that one can probe it? And it turns out that yes, you can use neutrinos from the DSNB to probe this sort of a thing. And in order to do this, we stay agnostic of as I said, we stay agnostic of the mechanism that causes this variation of masses. That can happen either by coupling it to some very light scalar, which can be the dark energy parameter, or it can happen due to a phase transition and so on, but we stay agnostic of it. The idea is we assume that the neutrino mass variation is basically parameterized by something like this. So for redshifts, for zero redshift, which is today, the neutrino mass is essentially what we say what the upper limit that we observe from Planck. So we have some value. But then as you go to higher and higher redshift, the neutrino mass gradually goes to zero following a function like this. So if you go to higher redshift, it basically goes to zero. Then there is some redshift which we call ZS, at which the mass switches on, and the width is basically given by this parameter BS. So this is just a very simple parametric form which characterizes this sort of a thing. We contrast this with the star formation rate that is shown out here. And as you can see that if the neutrino masses switch on at redshifts of order 1 or so, they would have maximum impact on the DSNB, because that is also when the neutrinos coming from the maximum amount of stars that you get, because this is the star formation rate. So for different redshifts, this can happen for different values. Now, I won't go into the details. I'm going to tell you what is the underlying physics that tells you that you can, in principle, use this to probe different redshift variations of neutrino masses. So the DSNB essentially is composed of neutrinos coming from different redshifts, right? All the way from the redshift of star formation. So all the way from redshift of 6 to today. So let us imagine we are detecting neutrinos from a supernova that went off at a redshift of Z1, which is much smaller than the redshift ZS when the neutrino mass switches on. So for all supernova that happens on the left side of ZS, neutrinos are massless. For all supernovas happening on the right side of ZS, neutrinos have a certain mass. So for example, for this guy, the neutrinos that are produced inside the supernova, for them, the flavor and mass eigenstates are identical because they are massless. So they are basically emitted as a mass eigenstate, because for them, there is no difference. So the mixing matrix is essentially diagonal. So they travel up to a certain redshift ZS as massless neutrinos, and then the mass switches on. And then you have your standard vacuum mixing that takes into play, and you basically get this neutrino. You can have a supernova that happens around this redshift, and then this is more interesting, because then essentially the neutrinos can have a mass. They can suddenly have a mass as they're traveling through the supernova. And this can have a different effect, because typically in these scenarios, the neutrino propagation is considered adiabatic, looking at the density profile and so on. But then this adiabaticity also depends on the mass and the mixing parameter of the neutrinos. So if the neutrinos masses are extremely tiny when they're traveling through the supernova, their propagation can in principle be a non-adiabatic propagation. And this can give you a different result on how much let's say electron neutrinos you get at the end of the neutrino traveling outside the supernova. On the other hand, if something happens on the right hand side, then this is just the standard stuff that we know. So this is just massive neutrinos for which the PMNS matrix is non-diagonal, and you get a different flavor and mass eigenstate combination. What this implies is that the final electron neutrino probability that you get at the Earth is not just a combination of the mixing matrix elements, but one also needs to take into account non-adiabatic hopping probabilities, which come up simply because the neutrino masses the neutrino masses are different once they're traveling inside the supernova and so on. And as a result, the net electron neutrino or the electron antineutrino flux that you get at the Earth would be different, simply because it's not just produced from supernovae like this, but it's also produced from supernovae where the neutrinos are massless, and these effects need to be taken into account. And in order to understand this, let's just try to solve the propagation of neutrinos inside a supernova to obtain the probability. And we do it as a function of the redshift. So in this plot, I show you the probability of the survival probability of the electron neutrinos as a function of redshift. And let's assume that the neutrino mass switches on at a redshift of 1. For higher redshifts, the neutrino mass is 0. For lower redshifts, the neutrino mass is what we observe today. And this is what we get. So you get a probability that has this interesting shape. And we can understand this analytically. So let's focus on neutrinos which are on the right-hand side of this. So for higher redshifts, where neutrinos are massless. Now, as you remember from the previous picture, for massless neutrinos, the flavor and the mass eigenstates are identical. So the PMNS matrix is unitary. So the massless neutrinos propagate all the way through the supernova up to vacuum until they reach a redshift of 1 when neutrino mass switches on. And then, of course, the PMNS matrix start becoming non-diagonal. And then you have a difference between mass and flavor eigenstates. So the final electron neutrino probability that you get at the Earth is essentially a product of the two PMNS matrices, right? So you have UK square times UKE square. So you convert a mass state to a flavor state, and then again you see what's the flavor state that you get at the Earth. And this turns out to be a number around 0.57, which is exactly this value out here. On the other hand, if you are considering neutrinos inside the supernova where the mass switches on and you have standard adiabatic propagation, then the survival probability is just given by the usual PMNS mixing elements, which are just these values. Interesting part is the following, that let's say you are in normal mass ordering, then the survival probability of electron neutrinos that you would expect is a factor of around 2%, just given by UE3 square. Contrast this to this value, 0.57, and you see that there is a large jump in probability. So you would expect to see a large enhancement of events for new E's in the normal mass ordering. And this is the signal that one can look for in principle. If you see this sort of an impact, then in principle, this can be attributed to a variation of neutrino masses. The effect is not very large for other cases, for example. So if you look at nu E bar, then the probability that you expect is around 0.67 as opposed to 0.57, and this difference is not very much. On the other hand, also, if you're in inverted mass ordering, then also this effect is not as strong because it's a factor of 0.3 versus 0.57. So in this whole study, the maximum impact only comes if you're looking at electron neutrinos and if your mass ordering is normal. In this case, instead of a survival probability of around 0.02, you get this big jump of around 0.57. And this is an effect that you can see. What this ends up doing is this ends up increasing your neutrino spectra in certain energy ranges. So for example, if you take a certain scenario, let's say the mass switches on at a certain redshift, then the standard DSNB spectra is basically given by these orange solid lines. If the neutrinos were completely massless, then the spectra would have been this dashed line. And then if your neutrino masses switch on at any point in between, the spectra basically starts increasing. And as you can see, for some values of when the mass switches on, which is basically less than 0.1 or so, then you can actually go even above this star formation rate uncertainty, and you can see extra large number of events out here. The downside, of course, is this lies in the ballpark value where you have a large reactor neutrino uncertainty. Remember, the reactor neutrino flux essentially kills you all the way below 10 MeV because this reactor background lies somewhere out here. So you can't really expect to see this enhancement unless you can reduce the reactor background, which is very difficult. But then we have an advantage. The advantage is that because the net flux is conserved, so if you have an enhancement in this region, you would have a suppression in this region, simply because we're not producing extra neutrinos. So the spectra just becomes more pinched. So an experiment looking for new E's can basically look for suppression of events in this range. And this can in principle be detected. So to demonstrate this fact, we showed an example for Dune. So let's say the neutrino mass, so Dune runs for 10 years, and the neutrino mass switches on at a certain value with a certain width. Then in principle, one can look for a variation of this. Then instead of this orange line, one can look for this line going down. So you can in principle have a suppression of events, which can also go below your star formation rate uncertainty. And this in principle might give an indication, but then it's just a suppression of events, right? There can be different new physics that causes a suppression of events. The correlation that one needs to look for is the following. You expect a reduction in the number of events in the electron neutrinos, because that in normal mass ordering, because that is what is maximally affected. But also an experiment that is looking for anti-neutrinos, for example, a new E bar, would not see any change, because by this argument that I showed out here, let's say in this, the anti-neutrinos essentially just get a change from 0.67 to 0.57. So there is not much of a change. Whereas for electron neutrinos, you get a change from 2% to 50%. This would be a big change. So any kind of new physics that essentially affects new E's and new E bar differently might be sensitive to this. But otherwise, if you assume that any new physics affects both these things simultaneously, a correlated signal would just be, you see a reduction in the number of events in electron neutrinos, and you see an enhancement in the number of and you see the number of events in the anti-neutrinos to be the same. So if both these two things remain the same, and if in principle, if you can reduce the star formation rate uncertainty, there is a way that one can probe this sort of a scenario. But of course, currently, one needs to be very, very optimistic. This still lies within the uncertainty region. But then this gives you an interesting way of probing, at least theoretically, whether if neutrino masses switches on at different times in different redshifts, whether the DSNB would be sensitive to this or not. So I think I'm almost out of time. So this brings me to my conclusion. So I hope I've been able to convince you that future measurement of the DSNB would basically open up a lot of avenues for neutrino physics. And in my opinion, this would be like the next giant leap from solar neutrinos and neutrinos from 1987, because this would be the next major spectra of neutrinos that we observe from a very large extragalactic sources. I mean, we have observed neutrinos from different high energy sources, but these are essentially isolated events and so on. Of course, a core collapse supernova is extremely rare. So this is probably our best bet to measure supernova neutrinos in the next decade or so, and to learn more about supernova properties. This, of course, is crucial for testing very, very extreme properties of neutrinos, which cannot otherwise be tested, simply because this gives you access to some of the longest baselines that's available. And as I said, a future measurement can in principle be used to test things like neutrino decay, whether the neutrinos are Dirac, Majorana, pseudo-Dirac, and so on. And even if you're too optimistic, it can also be used to test if neutrino masses switches on at a certain redshift or not. Things that I did not discuss is one can also use this to make some measurement of the Hubble parameter. So it's not, of course, as strong as a photon measurement, but you can put a neutrino measurement of the Hubble parameter on this plot where you show different measurements at high and low redshifts. And this, of course, adds to our philosophy of multi-messenger astronomy, where we do measurements so not only with photons and gravity waves, but also with neutrinos. There are also other constraints that are discussed in the literature, but I did not talk about, like constraints on star formation rate, on whether one can put constraints on what fraction of stars form a failed supernova, like what is the black hole fraction of it, and whether there are alternative cosmological models and so on. But I can discuss more on this if there are questions. So yeah, with this, I'll conclude. Thank you.
Thank you very much. Yeah, do we have questions, Roland? Go ahead.
Thanks for the interesting talk. I had two questions. So the first is, well, one, have you thought about what the explosion of Betelgeuse would mean? And the second question is, I didn't really understand how the measurement of the very, very small mass splitting works, because I think you were showing an oscillation pattern as a function of energy, but I'm worried that the sources are at different distances. So how do you not Yeah, how do you not sort of have some effective averaging?
Yes.
Because of the is it because you have such a sharp peak in the star formation rate at a certain redshift, or?
Exactly. Yeah. So
Okay.
so two things. So first is the Betelgeuse. If Betelgeuse takes place, then we don't even need to go into the DSNB, right? Because Betelgeuse is at 200 parsec. The data from 1987 was 50 kiloparsec or something. So you get a huge enhancement, and then all these things are secondary because you would have like tens of thousands of data from a almost galactic supernova. So that is probably the best case scenario. And Betelgeuse is also now showing a variation in its intensity, so that's probably something very good. So Betelgeuse would probably not Betelgeuse, if that takes place, then all this is secondary. That would be my statement, because all these studies can also be done with usual data from a supernova. The disadvantage would be, of course, we do not have access to such long baselines. So then also these studies still remain valid because they give you access to baselines which Betelgeuse would not give you. But then you would the advantage would be you would get a huge flux from Betelgeuse. So that would be the best thing that can happen. For the second question, of course, yes, as you said, this depends on the star formation rate. And of course, the oscillations, firstly, it's just like standard oscillations, but they're for a different delta m square. And the fact that they're coming from different distances would be taken into account by the fact that this oscillation, this base length is a function of redshift. But of course, because the star formation rate also peaks at a certain redshift, you would get maximal contributions from those neutrinos which are coming from around that redshift. So even if it does get smeared a bit, you would, I mean, this is just at the spectral level. Once you integrate this with the resolution and everything, you would expect some of this to get smeared. But the advantage is because these are drastic changes in the shape of the neutrino spectra, you would still have sensitivity to it.
Okay, thank you.
I think Teresa was next.
Thanks. I was wondering whether you could comment on whether dark matter direct detection detectors like Xenon or LC via the 7th channel could have any impact on this, or
yes,
just to learn.
There have been recent studies on this by John Beacom and others, and they do show that there are sensitivities, but of course, there are other issues with this, right? So because you are contesting against the other backgrounds as well, so it's currently very difficult. And also the other problem with that measurement, or rather the information that you do not get, is that these are flavor blind measurements. So you do not really have a measurement of the of different flavors, right? Because you get a net signal. So it does help you in detecting whether this exists or not, but you cannot do studies like this from a 7's measurement of it.
Thanks.
There was a question in the chat about whether you need to consider neutrinos from AGN.
They are much subdominant. What do matter more are neutrinos from failed supernovae, so supernovae which go into black holes and so on, and that can give you a subdominant contribution. That can give you a contribution which is comparable, not completely subdominant. So let me see if I have this. Yeah. So for example, if I look at the star formation rate out here, I essentially in this integral we go up to 50 solar mass or so, and this takes into account that we are not taking contributions from neutrinos from black holes. But in principle, you can have contributions from neutrinos from black hole, and then that gives you an additional contribution for heavier masses. And that fraction is roughly like 20% of the stars. 20 to 50% of the stars can go into black holes, and that can give you some contribution as well. We did not include that in this study, but in principle, one can do that as well.
Anyone else? So I might ask my questions then.
Yeah.
So regarding this varying neutrino mass, the cosmologically varying neutrino mass,
yeah.
Is there a way to constrain that just by looking at the supernovae themselves? I mean, does the neutrino mass have an effect on like the light curve of a supernova or something at different redshifts, or is it expected that you don't really have any effect on the supernova, like luminous signal from the supernova?
So the light curves is more tricky, right? Because the light curves essentially depend on the photon signal, and for these things, 90% of the energy is already taken away by neutrinos. So if you're just looking at an isolated supernova event, I do not think there is a way of probing this, because all you're seeing it something happening now, right? So even if the supernova happened some time ago, like some time back and so on, and neutrinos have been traveling over a long distance, this effect would not be so drastic, because for this effect to happen, you really need to take into account neutrinos from a lot of different sources that, which have been undergoing this effect. So probably at the light curve level, there would not be a change. But yeah, I mean, one can look into this, of course.
I was also wondering about just a general general question for kind of all the results you presented. You mentioned at the beginning, I mean, the computation of this flux is basically folding in, you know, the cosmological model and also the star formation rate and the collapse supernova rate and all of this. I'm just wondering, like, how are those uncertainties treated in general in your calculations, and are they sort of degenerate in some sense with some of the signals you'd want to extract?
Yeah, so in our calculation, we didn't. So there are very interesting recipes that are presented in these papers where one can treat this. So we took the simplest one, where we basically, you know, so if you look at these ranges that exist out here, we assume that there is like a 40% uncertainty in the normalization of this 1987, like from the DSNB spectra. So all the results, so this is basically this uncertainty. And all the results that we showed, like all the sensitivity plots, they basically take into account that this normalization uncertainty would exist. So if one can reduce this in, let's say, future measurements would basically reduce this, then in principle, these bounds get better. We did not take into account other sorts of uncertainties like systematics and so on and so forth.
Yeah, also this I haven't heard of this this like pseudo Dirac neutrino case where you have these sort of almost degenerate masses. Is this also a valid mass generation mechanism for the neutrino?
Yes, absolutely. So this is something that was, I think that it's become less and less popular nowadays, but it was quite popular in the 90s and so on. There are a lot of papers on this, and the advantage is, let's say you do not detect double beta decay signals and so on, can you always claim with a certainty that your neutrinos are Dirac? And this is one scenario where your neutrinos are essentially Majorana, because you still have a non-trivial Majorana mass, but then the signatures would not be seen in any terrestrial experiments, because the effect only comes up over very long distances. So this is one of these cases where lepton number is just very softly violated.
Okay.
It goes into the literature as, so it initially started off as quasi-Dirac neutrinos, and then quasi-Dirac neutrinos were in cases where the delta M, like the atmospheric and the solar mass square differences, were not yet well measured. And then if you just assume that these quantities are tiny, then they were known as quasi-Dirac neutrinos. So they're degenerate scenarios. But once you introduce right-handed neutrinos, it became known as pseudo-Dirac. So.
Okay. Yeah, well, that's interesting. The other thing I wanted, I don't know how much you can elaborate on this, but you had a comment sort of towards the beginning that there's this factor of 2 discrepancy between the core supernova rates calculated by the supernova themselves and by the star formation rate. What is that a serious tension people are worried about, or is this sort of something in the details?
So I think it depends on who you're talking to. So I talked to some of the people out here, and they think that this is probably just an astrophysical uncertainty and it would go away. But then there are some others who think that this is a serious discrepancy, and it probably points to the fact that we don't understand this rate of star formation very well, because one measurement is just doing this and the other measurement is folding in these 2 quantities and getting some estimate. So it of course depends on how you are parameterizing this data, and they believe that this is not completely well understood.
Can I've got a comment here actually. It's a bit you're just assuming a saltpeter IMF here, which is kind of old-fashioned, right? I mean, we do have better measurements of it now. I would have thought that could make some improvement, and yeah, I mean, I guess
other IMFs that you also have, these are basically inverse functions of masses, right? So I mean, I looked at the literature and there were like 3 at the time when we were working out, but I'm sure there might be more also. But I think I'm not sure how sensitive it would be to the overall computation, because as long as it goes as some inverse power law and it's not drastically different from 2, like it's not like 1 over m⁵ or something, I don't expect this to be a very strong effect.
Yeah, well, I mean, I think you could make a difference in the supernova rate core collapse supernova rate per unit mass of stars formed at the level of 2.
I see. Okay.
Yeah. So
just with this rate, right?
Yeah.
Okay.
It might just be worth checking that.
Okay.
Because most of the modern IMFs, you have a flattening at the very quite low mass scale, like below the solar mass scale,
okay.
and so you form less total mass in stars for given supernova rate. Is that the right way to say it? Something like that.
Okay.
Yeah, I mean, and I guess also there's the question over what's the lower bound on the integral in the denominator there, whether that sort of 8 solar mass as the threshold for producing the core collapse supernovae. Yeah, people argue about that as well.
Right. So in principle, you can consider these electron core, low mass iron, magnesium core supernovae as well. So the magnesium, oxygen, neon core supernovae, and in that case, this can go like to 5 solar masses, for example. But just for the standard iron core ones, 8 solar mass is like a standard ballpark value.
Yeah, that's right. Yeah, you can also have a similar process where you have accretion onto a oxygen neon white dwarf.
Exactly. Yes. For those, this can be small.
That's right. Yeah. Thanks.
Well, I think might have exhausted the questions. I did have one final a question about what is maybe a more technical point. On the, can you flash up the formula for the flux, like the first one you showed?
This one?
Yeah. So how do you treat the fact that supernovae of different masses will have slightly different emission spectra? Shouldn't this sort of spectrum be inside of the mass integral somehow?
Yes. So we assume that this is taken into account through the normalization, but in principle, one needs to also take into account that. But that's probably once you detect it, you can look into those fine tunings, because it's not going to make a drastic difference out there. But you're right, because it would change depending on the masses. The normalizations would change, but as long as the shapes don't change much, we assume that this would be taken into account by this.
Yeah. Okay. Cool. Yeah. All right. So I think that's